Hi, students. We're going to get started talking about the atomic timeline. And I just wanted to share with you that you will see a series of contributors and discoveries from scientists that has led to the development of the atomic theory. And the atomic theory encapsulates our current understanding of the atom and its structure. And the development of this theory illustrates the nature of science. So there are a few scientists that you really do need to be very well aware of and what they contributed to the atomic theory. And we're going to be going over these select scientists. And when we get to certain models, I want to pause and talk about some other things as well. But anyway, this is your Google Doc that you'll be filling out as we go. And if you notice, there is a place to write in a description and then to do a drawing. And you can use Google Draw, or if you want, you can, print this out and do your own drawing and then submit it to me that way. So it's really your choice how you want to fill it out. So let's go ahead and get started. So there is a link here that goes through a visual timeline for you. If you click on this link, it's actually pretty good, but there's a lot of scientists here that you will not need to remember, at least at this level of class. But it definitely does show you a good visual. So I suggest, taking a look at it, and it goes vertically. Okay, from the oldest discoverer or thought about an atom to the most current model, which is all the way down at the bottom here with Murray, Gell-Mann, and Zweig. Okay. All right. So Democritus, he was the first person that came up with an idea about an atom. And he was a philosopher, and he believed the universe was made of invisible units called atoms. And he named them atomos back in 400 BC. And Aristotle said, you know what, quote unquote, he's a quack. But it took 2,000 years for him to be proved right. 2,000 years. So on your notes, if you could please fill out where I have the red is where the blank spaces, the words for the blank spaces go. And then your drawing is just a simple round atom that's filled in. It's a solid sphere. And the beauty of this presentation is you can pause it at any time if I'm going too quick for you, and you can fill it out at your pace. All right, the next person was John Dalton, and we mentioned him a little bit when I showed you the slideshow on properties, physical and property changes. And he was a British school teacher, and he wrote the first atomic theory. And the reason why he was credited with the first atomic theory is because he ran experiments on substances. And some of his conclusions were that all elements are composed of tiny, indivisible particles called atoms. Atoms of the same element are identical, and atoms of one element are different from those of any other element. And that atoms of different elements combine in simple whole number ratios to form chemical compounds. And in chemical reactions, atoms are combined, separated, or rearranged, but never changed into atoms of another element. So there's one thing that he was wrong about elements of the same type being identical, and that is the word isotopes. It's a type of atom that has a different amount of neutrons in its nucleus than the majority of those atoms of that element. So we'll talk a little bit more about isotopes as we go through our study in chemistry. So he got credited with the billiard ball model, okay? And this theory proposed that matter was composed of small spherical particles, but evidence was later gathered that matter was composed of even smaller bits. So on your sheet, you can write that he had the same ideas as Democritus, but added an idea that there's a different atom for each element. and two or more atoms form compounds. And he was credited with the first atomic theory. So you're drawing, you're going to draw 3 different atoms of an element, and you can draw them any way you want as long as they're different. My model is just, showing hydrogen with a round dot in the center, and then oxygen with no dot, and then nitrogen just split down the middle. But you can draw it any way you want as long as those atoms are different looking. That was his main idea there with that. So we have new evidence now. During the 1900s, there was 2 other researchers and scientists, Rutherford and Thomson, and they said that atoms, Rutherford's contribution said that atoms have positive charges, and Thomson said there are negative charges throughout. And those charges interact, okay? As you know, like charges repel and opposite charges attract. So revisions had to be made to Dalton's theory. So Thomson was credited with the plum pudding model or the chocolate chip cookie dough model. So if you were to look at, the atom now, the bulk of the atom is like the dough part, which would be like the chocolate chip cookie dough. The dough part would be positively charged. And then those little chocolate chips that were sprinkled in between there would represent the electrons, and they would have a negative charge. And he did an experiment with a cathode ray tube to discover the existence of an electron. So this model did keep Dalton's key ideas intact. And here is what that cathode ray tube somewhat looked like. So the conclusions from this study were that the cathode rays had identical properties regardless of the element used to produce them. All elements must contain identically charged electrons. Atoms are neutral, so there must be positive particles in the atom to balance the negative charge of the electrons. And electrons have so little mass that atoms must contain other particles that account for most of the mass. So on your sheet, you're going to write that an atom is a positively charged sphere with electrons, with the negative particles scattered throughout, and that he used a cathode ray. And then your drawing, you can just draw, a round circle with positive sphere, and then the negative electrons are throughout. And if you want to put plus sign in that bulk of that area, you may. Ernest Rutherford came along a little later, and he discovered a huge flaw in Thomson's idea and through his experiments. And so Rutherford did what was called the gold foil experiment, and he's famous for that now. He discovered the nucleus and the positive protons, and he's the one that said, hey, you know what? An atom is mostly empty space. Empty space. There's nothing there. We still didn't know anything about neutrons, but he did this experiment and he shot alpha particles through a thin gold sheet. And what he found was most of those shots went straight through the gold foil. A small amount were deflected. So then hence the atoms must be made of mostly empty space with a very, very small dense nucleus. As a matter of fact, today we still believe that, that the nucleus is really, really tiny. So if you think about a marble in a football field, and the outside area of the football field being where you would find the first electron, that marble would represent the nucleus of the atom. Okay, so everything in between the outside of the field and that nucleus, there's nothing there, empty space. All right, so and this is kind of like what happened with the arrows I'm showing you here. That's the alpha particles that are just going right through the gold foil. Okay, and so that nucleus of the atom is positively charged, and most of those particles would just go right through. Every now and then, the alpha particle might hit the nucleus of the atom and get deflected back. But most of the time, 99% of the time, they went straight through. So he was able to conclude that the atom is a dense positive core, and the rest is composed of mostly empty space with the occasional negatively charged electron. And so this model completely changed the definition of the atom. So his conclusions were the nucleus is small, it's dense, and it's positively charged. So on your drawing, for your drawing, you're going to draw a very small nucleus that's positively charged, and then you're going to draw negative electrons outside the nucleus. He did the gold foil experiment. Niels Bohr was our next scientist. He discovered that electrons exist in several distinct layers or levels. It's kind of like the Johnny Neutron model of an atom. And they travel around the nucleus like planets. The electrons travel around the nucleus like planets travel around the sun in distinct orbitals. And these electrons can jump between the levels with energy either being added or released. So he proposed that the electrons revolve around the central positive nucleus like planets in a solar system. And they are quantized, those energy levels. And what that means is that there's no energy between the steps, and the steps represent the orbits. Kind of like when you think of stair steps, when you're going up and down stairs, those steps are quantized, which means they only have certain places where you can stand. That's the same thing with electrons. Electrons can jump, up and down the energy levels, but they don't exist in between those energy levels. So on your paper, you're going to draw a positive nucleus with orbits that contain the electrons. The cloud model is the current understanding of the atom based on quantum mechanics. And now the electron cloud model best represents our current understanding of the atomic structure. The electron cloud model describes the atom as containing a dense nucleus of protons and neutrons surrounded by regions of space, clouds, where electrons are most likely to be found. Okay, so the Bohr model that I just showed you is inaccurate and doesn't depict the 3D nature of the atom. It implies that electrons are in static orbits. We do know now they are not, but we do use the Bohr model a lot in 8th grade and in high school to show the structure of the atom, like where the protons and the neutrons are and where the electrons are in their energy shells, okay, or in this case, orbitals. But just keep in mind that this model of the cloud model sees the electrons not as individual particles, but behaving like a cloud. And the electron can be anywhere in a certain energy level. So on your paper, you'll draw like this small nucleus, and then the first energy level here around the nucleus, you just put like dots all over the place, like bees buzzing around a beehive. And the probability of the electron being in that place is pretty good, and not so much throughout the empty space part of the quantized atom. So here the electrons can be found in these shells, we call it, okay, or energy levels, where I'm pointing. We still have a positive nucleus. And then where you see the white space, those electrons are still quantized, and no electrons can be found there. So like I said a little while ago, most things we do can be explained using Dalton's or Bohr's model, but this model is the most accurate, but it is very complex. Chadwick came along and he did an experiment with beryllium atoms with alpha particles, and he's the one that discovered the nucleus of the atom, okay? And the way he did it was an unknown amount of radiation was produced in these experiments, and he interpreted this radiation as being composed of particles with a neutral electrical charge in the approximate mass of a proton. So we know this particle is now known as the neutron, and with the discovery of the neutron, an adequate model of the atom became available to chemists. So on your drawing now, you're going to draw like a Bohr model. It's a modified, I call it a modified Bohr model. Obviously, we know the electrons are in clouds, not orbits, okay? but we put them there for simplicity. But inside the atom nucleus, you'll have protons and neutrons. So use different colors to represent, or put a positive sign in the blue subatomic particles and an N in the green ones. And then you have your orbitals here, are energy levels. The first energy level can contain up to 2 electrons. And then the second one, in this case, has 1. And remember that atoms are neutral particles. So if you put 3 protons in the nucleus, you need to have 3 electrons outside the nucleus. Gell-Mann and Zweig came up with a quark model. And quarks are subatomic fractional particles that you'll find on the protons and neutrons in the nucleus of an atom. And they can either be positive or negative fractional particles. There are 6 types with funny names, and they're grouped in 3 sets of 2. So when you look at the atomic model now, it's the same as the cloud model, except the protons and neutrons are composed of quarks. And so in here, I know this is a really inflamed, large nucleus. We know the nucleus is much smaller than this, and these drawings are really out of scale. And as a matter of fact, if you were to draw, like put a pin, like just a take your pen and just put a little dot on your paper that you're working on, if that represents the nucleus, outside of your paper, you couldn't even draw the first energy level for the electrons, because the nucleus is such small space. But here, I just want to show you inside the protons here, in this particular red one, represented with a red color, there's 2 up quarks and 1 down quark. Okay, and then in the neutrons, there are 2 down quarks and 1 up quark. And remember, the down quarks charge here are -1/3, and the up quarks have a positive charge of +2/3. Now, you're not going to be responsible for knowing the charges of the quarks and all that. What you need to know are what you drew on your paper, okay? The little description and the drawing. So make sure your drawings are accurate. We're going to work more on this next class, but make sure that you complete it and turn it in as an assignment for credit.